Now for a summary of what we covered in this section on prime numbers. We defined a prime to be any integer bigger than or equal to 2, divisible only by itself, and 1. And then we saw that the primes were very natural in the sense that every positive integer is a product of primes in a unique way up to reordering. The proof of the existence of a prime factorisation was straightforward. We simply took an integer. If it was not prime, we wrote it as a product of two smaller integers. If either of them were not prime, then we kept factorising until we ended up with primes. It was as simple as that. However, the proof of the uniqueness was not so straightforward, and it introduced a number of interesting ideas which are useful in other situations. In particular, we first proved the Euclidean algorithm. The Euclidean algorithm was a means of finding the greatest common divisor of two integers a and b without actually factorising the integers a and b. And this is very useful later on when we're having to deal with very large natural numbers with, say, 300 digits or so. The extended Euclidean algorithm then followed from the Euclidean algorithm. So the Euclidean algorithm was proved by essentially continually applying the division algorithm, and then the extended Euclidean algorithm, which showed that the greatest common divisor of two integers a and b is the sum of multiples of a and b, where one of those integers s and t will be negative. And that was proved by working backwards through the Euclidean algorithm, which was used in the first case to find the greatest common divisor of a and b. We then used the extended Euclidean algorithm to prove the prime divisor theorem, which said that if p is prime and p divides ab, then either p divides a or p divides b, and of course possibly both. The proof is quite interesting. If p divided a, we were done. If p does not divide a, then the greatest common divisor of a and p must be 1, and then by the extended Euclidean algorithm, 1 is sa plus tp for suitable integers s and t. We multiply through by b, and we get b is equal to sab plus tpb. But p divides ab, therefore it divides this term, and p certainly divides this because p is a factor. Therefore, p must divide b. So we've proved the result that either p divides a or p divides b. And then, using this fact, it's relatively straightforward to show that any two factorizations of a natural number n must be the same, because if you take two factorizations, take a prime from one of them, it divides the other factorization, and therefore that prime must equal one of the terms in the other factorization. And finally, we gave an example to indicate that uniqueness is not really obvious. We introduced the idea of an even prime. This is not a standard notion, by the way.